Jim is with AT&T, as you can see here, and he's also with SANS. He's been an instructor with SANS. Currently, I get to work with him specifically with regard to our Forensics 610 class, which is all about reverse engineering malware. And he's been somebody who we can always rely on to to really distill down a lot of the complex material to something that even somebody who's relatively new is able to really grasp and really understand. So it's always been a lot of fun to work with him and to let him kind of spread that knowledge in that way. We'll go ahead and we'll get it turned over to Jim real quick here, and then we will kind of reconvene a little bit later on. But he's going to be talking to us today about if at first you don't succeed, try something else. And it's really kind of the best skills I think anybody who's in forensics can actually have, which is, we get asked a question, what is the answer? And so many times it's not really a matter of answering the question, it's figuring out what the question really means, and that takes a little bit of this kind of succeed fail type cycle. So anyway, Jim, I'm very excited for this. Glad to bring you in. Thank you for sharing your time and expertise. And without no further ado, it's all yours, sir.
Thanks, Phil. As Phil said, I am Jim Clausing. I work for AT&T at my day job, and I'm a SANS instructor. And as the slide shows, if at first you don't succeed, try something else. The agenda for the talk is really pretty simple. I'm do a little bit of an intro to set the stage, but I really just want to tell a story. And then hopefully at the end, there will be some time for questions if there are any. But quick little bit about myself. At the day job at AT&T, I'm a Forensicator and malware analyst. I also teach Forensics 610. In fact, I'm in the first week of a 3-week run, so if any of my students are watching, I'm glad you could join us. I'm also a cyclist. I have a recumbent bicycle that I love to ride and have about 12,000 miles on it. My Discord avatar is me on my bike. And I'm an instrument-rated private pilot, which I'll talk about, mention here in a little bit. So, as forensicators and malware analysts, we don't get to choose when we're going to have an incident. They kind of happen. And so, incident happens, we get called in, we have to do our thing, incident is over, maybe we've got a little downtime between cases, and that's a good opportunity to catch up on some project work, update and refresh our tool sets. It's also a really good opportunity if we haven't been able to practice some of our skills to take an opportunity and get some practice in. As a pilot, an instrument-rated pilot, I don't fly in the clouds all that often. I don't fly in instrument conditions all that often. So in order to remain proficient, I try to fly with an instructor at least once or twice a year, just to knock the rust off, to make sure I'm not getting in any bad habits. Well, the same should be true of us as professionals, in forensics and malware analysis. If we don't practice and we don't keep our skills sharp, we get rusty. We become less than proficient. So, to set the stage a little bit for this case, or well, not a case, but for this malware sample that I'm going to talk about here. Last year, around Labor Day-ish, I had some downtime, and I hadn't had a really serious malware case to work in a couple of months. And I was made aware of a sample that had a kind of interesting little packer to it. It was new to me. I don't know, maybe others had seen it before. I hadn't seen any write-up on it. So between cases, seemed like a good opportunity to get some practice in. And a couple of my colleagues also decided to take a look at this, and we decided we'd each look at it independently and, see what we could see. A little competition, friendly competition between the team is always a good thing. So I got a hold of this packer, of this malware sample. And as I normally do, I started my preliminary examinations, looking at static properties of the sample. And so I threw it into PE Studio. It was a Windows executable. I threw it into PE Studio. Love the tool. If you've never used it, do it. And one of the first things I noticed was this, in looking at the sections, there was this section called .pe. And the PE Studio, the tool, flagged that as suspicious. That's a section that I had seen in some other samples where they would hide an embedded PE file, another executable or a DLL or something. So that got my attention. Okay. So I look at some of the other properties, and I go down to the version information, and I'm looking at listdemo.exe. Something about that just sounded familiar, but I couldn't really place it. Okay, fine. So I move on a little more, and I start looking at the strings, and you got your normal, not too interesting strings up at the top. And as I scroll further on down through it, eventually I run into the section where I've got a number of strings, one after the other, and PE Studio says they're all 260 bytes long, that look like base 64 encoded something. Okay. Hey, that gets my attention. Base 64, what are you trying to hide? So I continue on my normal approach to malware analysis. I did some behavioral analysis. I just let it run, and it didn't drop anything on the file system. I didn't immediately see it injecting into other processes. So, okay, well, maybe I'm not going to learn a whole lot about it with simple behavioral analysis. So then I move on to static code analysis. And this is more or less the process that we teach in 610. That's what I do when I normally analyze malware. So I started static code analysis. I threw it into the disassembler. Actually, I threw it into Ghidra, so I also had the decompiled code. But I threw it in the disassembler, and I started looking around at the various functions. And now this list demo is becoming even more familiar. I swear I've seen this list demo as a sample project for some integrated development environment, some IDE out there somewhere. But I Googled for it and couldn't find it. But I swear I've seen this someplace before. Looking through the code, and the code really is, the shell of it is this list demo. It goes through all of the gyrations to create a box, put a list in it with a scroll bar. The only thing it doesn't do is it doesn't finally reveal the box, the window with the list in it. Okay. So I move on past that, and I find some code that I think might be the unpacker. And as I'm looking through this code in the disassembler and the decompiler, there's a lot of garbage code in here. What do I mean by garbage code? They'll allocate a chunk of memory, they'll do some computation, maybe they'll shove something in that memory, and then they'll throw it away. They won't use it for anything. So it's essentially wasting cycles, but I suspect that the code was placed in here to make my job more difficult as an analyst. And this is not unusual. If you're not familiar with malware, the attackers do this all the time. So maybe I could have figured it all out doing it statically, but that would have taken a lot of time. So let's move on. Let's try another one of the techniques that we actually talk about in the class. Let's try to unpack it with the debugger. And the goal here is to try to figure out when the unpacker is done unpacking and when it's jumping to the beginning of the original code, what we call the OEP, or the original entry point. And so, we start to think about what activities might the packer do towards the end of the unpacking process. And one of the things that the malware often needs to do when it's unpacking a sample is to rebuild the imports table, because the imports of whatever the packed executable were are not necessarily going to be reflected in the imports of the packed executable, because all you need in the packed executable is the stub that does the unpacking. And so before you jump to the unpacked code, you need to make sure that the Windows APIs that the unpacked code is going to call are available to it. So one of the ways that you can think to look for the packer unpacking and setting up the imports table is you watch calls to load library A or load library W, get proc address. So I started out in the debugger and I single-stepped around through it quite a bit, and then I set some breakpoints and saw it doing these calls to load library. And I found a chunk of memory in, a high address chunk of memory that had been allocated earlier on by the unpacker. And in there I saw a DLL name and then a bunch of names of API calls with space after them. And the code would go through, would find the DLL name, would do a load library to load that DLL. Then it would look at these API names, call get proc address, and take the results of that and shove it into the space after the name. Okay, this is setting up the address table. Excellent. I followed this a while and I saw it filling in all of these gaps, got down to the end, and I found the point where it jumped to an address up in this high address space block of memory that it had allocated earlier on. Okay, cool. Worked just like it's supposed to. I found the jump to the original entry point. I take the jump, and now I try to dump it. The techniques that we talk about in class, not particularly important for this. And my dumping fails. First I try just dumping the address ranges where I think the executable has been unpacked, and there's a lot of interesting information there, but I can't quite get it to work again as as a regular, executable. I can't throw it in. Well, I can throw it into PE Studio, and there's some things missing. I can't double click on it and run it. Okay. So then I try the other technique, another technique that we talk about in class. Let's just dump the memory space of the whole thing, and then we'll try to, fix up the PE header to point to the unpacked code and try to get the import address table straightened out. And this still doesn't work. And at this point, I'm reminded of a quote that we've probably all heard that's attributed to 18th century Prussian Field Marshal von Moltke, that no plan survives encounter with the enemy. Yeah, my first plan of attack didn't work. My second plan of attack didn't even work. So now I've got to figure out, is there some other way that I can unpack this? Because what I'm really interested in is, what does the malware do? Well, that's in the packed version. So I think back to the stuff that I saw in PE Studio. I saw that .pe section, and I saw those base 64 encoded strings. Thinking maybe that's where I need to start looking. Okay. So I go back and I see in PE Studio that the .pe section starts at offset 39000 hex. So I throw the whole thing into a hex editor, and I go find address 39000, and there are a bunch of nulls there. Okay. That's not particularly useful. So I scroll on down a little bit, and I find a little bit later the end of the nulls. And what is at the end of those nulls? The base 64 encoded strings that I saw before. Okay, so my idea is looking promising. This section contains a base 64 encoded something. So how do I pull the base 64 encoded stuff out? Well, one of the nice tools, and we talk about it in class, written by a friend of mine, Didier Stevens, base 64 dump. And I run base 64 dump with the default settings, and there are 400 some odd strings in there. Finally, I realize if I ignore those that are less than 40 characters, I get down to 2. And one of them, the one that starts with YG capital I, that's the one that I just found in the .pe section. I notice here that it's 55,532 bytes long. Okay, good. I actually did take a look at that other 7,000 byte string, and it turns out that that wasn't related. It's an artifact of the way I acquired this sample, so it had nothing to do with the malware itself. Okay, so I could use this tool to extract and base 64 decode the string. But I decided, and in the past, maybe I would have done that. In the abstract for this talk, I talked about going old school. And 10 or 12 years ago, that's what I would have done. I would have extracted it using maybe this tool or something like it. And then I would have started writing a whole bunch of scripts. Perl scripts, cut, Linux cut commands, awk, sed, all that kind of stuff. It would have been Perl 10 years ago because I've been programming in Perl since 1989, so that's what I'm familiar with. And so I would have done that. These days, though, I like another tool. A big thank you to British Intelligence, GCHQ, for sharing CyberChef with us. If you're not familiar with CyberChef, you should become familiar with CyberChef. But I decided I'd use CyberChef this time. So I went back to my hex editor where I had put the binary earlier, and I selected out. I started at the top where I found the first non-nulls, went down to the end of that block, copied them out of there, pasted it into Notepad, and I had this block of base 64 encoded stuff. And sure enough, this block was 55,532 bytes long, which is what base 64 dump had shown me. So, okay. So now, rather than writing my own scripts where I pipe together, transformations until I get something working, I decided we'll throw it into CyberChef. And CyberChef has a recipe that you just drag on there to base 64 decode, so from base 64. And I added the recipe to hex because binary, I can't read binary. Doesn't represent well on ASCII screens or UTF-8 or 16 screens. And I started looking through the patterns in, the hex representations of the bytes in the decoded blob of whatever. And relatively soon, in that red box there on the screen, I discovered this stuff. There's a lot of repetition here, but it's not exactly completely repetitive. In the first line there, we've got BD819D84. In the second line, we've got BD819B84, and so on. So that there are one-offs all over in here messing up the pattern. But if you're at all familiar with PE executable, PE file format and executables in the PE format, at the beginning of a Windows program, there are a lot of nulls. There's MZ, and then there's a data structure that's got some sizes and some pointers, but then there's some nulls in there. There's the beginning of the PE, or the stub. This program cannot be run in DOS mode. We've all seen that. And then there are a bunch of nulls after that. So I got thinking, could this be as simple as an XOR? Malware authors do this all the time. Maybe this is simply XOR with a bigger key. And we see XORs with 1 byte keys all the time, but maybe this one is XOR with a bigger key. Okay, cool. But there are some one-offs in here. But often at the end of an executable, you'll see padded out with nulls to the end of a block or something. So I decided to go down and look at the bottom of that. And when I scrolled down to the bottom, I did in fact find a block that had this repeating pattern and then eventually some actual nulls. So I looked at this and I counted it up, and I figured out that the repeating pattern was 13 bytes long. Okay. So I took the last 13 bytes, and CyberChef has a simple XOR recipe in it. I took these 13 bytes, threw it in there, disabled the 2-hex recipe, and I got gibberish. Okay, well, maybe it's an alignment problem. So I started rotating 1 byte at a time, and I rotated it right. I could have gone left. I guess it didn't matter. And I rotated it, and after I rotated it 4 bytes, voila, I had something that looked really familiar. I got MZ. I've got this program cannot be run in DOS mode. But there's some stuff in front of it. So, okay, let's throw in the 2-hex recipe, and let's try to figure out how much junk there is in front of it. And for those of you who've been doing this for any length of time, the hex representation of a capital M is 4D. The hex representation of a capital Z is 5A. So I found the 4D 5A and determined that there was 24 bytes of stuff in front of it. Okay. So let's strip this 24 bytes out. I'll undo the XOR, but go back to the hex representation, grab that, pull it over to Notepad++, cut those 24 bytes out. I could have cut it out in the hex editor too, but anyway, in this case, I did it in Notepad++. Now, I had determined that the key was 13 bytes long. 24 is not a multiple of 13. 26 is, so I've figured I have to rotate 2 bytes further. Cut this out, put the hex into CyberChef, convert that back to binary, XOR it, rotate the key around, and voila. Now the key, when I was actually doing this, I had all the spaces in it. To make it look nice on the slide, I took the spaces out, but okay, cool. Very nice. Now this took me a little while, but it's a pretty straightforward process. The resulting executable here, the resulting file is 41,623 bytes long. Very nice. So let's take a look at this. I throw this into PE Studio, and yeah, it's got some interesting strings in there. Maybe some of these are IOCs. You know, run DLL 32.exe running shell 32.dll with ordinal 61. I don't know what that call is, but maybe that's a way to run a command without spawning a command shell. 51.81.9.201, is that an IP address of a command and control server? All stuff that might be useful as IOCs that we can look for to see if this malware is in the enterprise someplace. Look at the imports. Got Internet Connect, HTTP send request. Okay, so it's got the capabilities of communicating out to the internet. Map virtual key A, set Windows hook XW. Write file, create file. It turned out that the payload on this one looks like a keylogger. Now, we had done and calculated an imp hash, the hash of the imports table, and done a search on VirusTotal for that impasse, and we found about a half dozen samples, downloaded them all, and took a look, and they were all the same shell with a different payload. The .pe section was different, but the rest of the file. So this was a packer that was being used at the time, by some actor. Not sure how, what it was being used for, but so, okay, if this is a packer that's being used out there, then why don't we automate the process of extracting the packed executable? It was a fairly straightforward process, a 9-step process. We can write a script to do this. So a colleague of mine wrote a Python script to do this. It locates the .pe section, figures out where that starts in the code, jumps out there, throws away any nulls, pulls out the base 64 code, strips out the first 24 bytes, goes to the end, takes the last 13 bytes, rotates it a little bit, does the XOR, writes out the file. This packer was meant to be script, the decryption of this is meant to be scripted. And great. In the last 8 months, I haven't seen a single match for that impasse in VirusTotal. So this packer was being used for a little while, turned out to be an exercise that was mostly useful for me getting practice. But I guess the real point of this, and hence the title of the talk, it goes back to that quote from Field Marshal von Moltke that no plan survives encounter with the enemy. My first plan of attack, was to just look at the code statically. And I may have eventually been able to figure that out. In fact, I think one of my colleagues actually did manage to work through all that garbage code, but he had more patience than I do. My second plan was to go with the debugger and then dump it out of memory when I got to the OEP. And again, I might have, with another few hours, maybe I could have figured out what my issues were with the executable that I finally dumped out. But it turned out that this particular packer, fortunately, was a relatively simple one. And, just took stepping back a minute and going and attacking that .pe section and the base 64 strings that I saw up front that had gotten my attention. And in fact, I believe that's how one of my colleagues attacked it. We all ended up in roughly the same place, using, going our own different ways. So, yeah, I guess the moral of the story is, as forensicators, as malware analysts, we need to be flexible. We need to be willing to shift gears when we run into a brick wall. And with that, we're running close to the end of time. I don't know, Phil, if we've got time for any questions or not.
Well, there's one in here that I wanted to think you could probably answer pretty quickly. Do you have a favorite tool when you went back earlier on and you said that you tried to dump the binary? Do you have a tool that you prefer for using that, or any particular workflow that you'd be able to reference quickly?
Well, we do it in Forensic 610 from the debugger. Sometimes I can just dump the memory region and it works. Sometimes we use Scylla and then adjust to try to recreate the imports table and clean up the PE headers. Those were what I was trying here. But that's really it for as far as, I don't have a favorite, just use Scylla.
Sure. No, that makes sense. And, sometimes it's not a matter of needing something different. If you got a tool that works well, I've got screwdriver sets I've probably had for 20 years that work just as well as they used to. There's no need to replace them with the shiniest, latest, greatest if they do the trick.
Exactly.
Other question came in, is the script publicly available? Can you just go back one to your...
yeah, you can go back there. So yes, the script is available up on GitHub. Since it was produced at the day job, it's under AT&T's GitHub, not my personal one. But yeah, the script is there if anyone wants to take a look at it. It's a little embarrassing. It's not all polished, but it does the job. So
I always say the difference between coding and developing is that when you're a developer, you're willing to, I sometimes will say, like, share your code with others. Obviously we get into a position now where a lot of us are sharing code, even though it's not in its perfectly polished, refined form. So I do the same thing. Absolutely.